Orbital filling diagrams help us understand where electrons are located in the atom and what shapes they take. We're going to start with an orbital fill order that you should understand from looking at atomic orbitals. And I've drawn them as single lines on which we're going to put electrons. You may also see them drawn in your textbook as boxes, often sort of side by side like this. They represent the same things. I like the diagram on the left because it emphasizes the relative energies, or that the 1s is lower energy than the 4p. As we're adding electrons in, we can predict or use these orbital filling diagrams to predict the locations of electrons in the ground state. Okay, the ground state is the lowest energy state, and for an example, we might have a single electron there in the 1s orbital. This would be in the ground state. If we shine light at the electron, we can promote that electron, or shine light at the atom, we can promote that electron to a higher energy state, maybe move it up to the 4s orbital. Okay, this isn't the ground state. This is what we would call an excited state, and the rules I'm going to talk about in this video won't work for predicting where electrons are located in an excited state. Okay. There's going to be 3 rules that we use to talk about how we fill these up, and the first one is AufBau. That's not a D, AufBau. And this is German for build up, is we're going to start by putting electrons in the lowest available open orbital. Okay, so we put our first electron in that 1s orbital. The second one I want to mention is called the Pauli Exclusion Principle. Pauli is someone's last name. And what the Pauli Exclusion Principle says is that no 2 electrons can share the same 4 quantum numbers. Now, the first quantum number was the principal quantum number, that one that describes size, how far away from the nucleus it is. The second quantum number, let me move up here. The second quantum number was the p. It describes shape, and that p is a letter representation of the angular momentum quantum number. The third quantum number is describing the orientation. So the p has 3 orbitals in different orientations. Each of these is a different magnetic quantum number. And the fourth quantum number we're going to talk about is spin, or magnetic spin quantum number. And we're going to represent those by an up arrow and a down arrow. Okay, so this would represent the plus 1/2, and this represents minus 1/2. Now, I'm drawing these carefully as single barbed arrows. We use single barbed arrows to represent single electrons in chemistry. When we draw an arrow with 2 heads, that's representing 2 electrons. So I'm going to draw that. Your instructor may or may not be picky about that. The third rule that I'll talk about is called Hoons Rule, another guy's last name. And this takes place when we get to these p orbitals. So AufBau principle says the first electron goes in the lowest. The second electron is also going to go in the lowest energy, and that's the 1s, but it can't have that up spin. That has already been taken, so the second electron has to have that down spin. The third electron would like to go in the 1s, that's the lowest orbital, but it's full. There are no more spots by Pauli Exclusion Principle, so we need to go to 2s. That is the lowest available orbital. By convention, you always put the up spin in first. And there's my 4th electron and my 5th. Now, this is where Hoons Rule comes in. Hoons Rule says we'll place single electrons with up spins in each degenerate, meaning having the same energy, orbital before we pair them up. These 3 orientations of p orbitals are degenerate orbitals, and so what it's saying is that the 6th electron will go here, not here. Okay, so the 6th electron will go with that up spin in another of the degenerate orbitals. There's 7. Now that we've filled those up, we're going to go back and pair up 8, 9, 10. Okay, so that's what Hoons Rule is. And following these rules, we can put all the electrons into an atom. and get the ground state electron configuration. So let's try phosphorus. The first thing you want to do in these problems is figure out how many electrons you're dealing with. And in this case, a neutral phosphorus atom has an atomic number of 15 protons. If it's neutral, it will also have 15 electrons. Okay, and so we just start putting them in. AufBau Principle says start with 1s. By convention, we start with the up spin. The second electron, 1s, is still available if I use the down spin. 3, 4, 5. Now, Hoons Rule says 6 is an up spin, not paired. 7, 8, 9, 10, 11. All those in 2p were paired up. 2 electrons on each orbital is all I can do. So that's 11, 12, 13, 14, 15, and I stop. I've reached 15 electrons. Now, if I'm doing an ion, I would then either take away electrons or add more, depending if it's a cation or an anion. But perhaps here you can see or recognize why phosphorus forms a 3 negative charge as its stable ion. There's 1, 2, 3 more electrons that I can add to this atom before that 3 shell is full. Okay, and we'll see this pattern a few more times, but that's how we do the orbital filling diagram. Now I want to note some terms that we use for different electrons in this orbital filling diagram. All of the electrons with the highest principal quantum number, in this case 3, we're going to label as valence electrons. Okay, the electrons that are not valence electrons are core electrons. I want you to think about this as an onion. The valence electrons are the ones near the surface. They're the ones that can interact with a nearby atom and that are going to participate in bonding. The core electrons are those inner electrons, and they are not significantly influenced by what atoms are nearby. They're influenced primarily by the nucleus. And so we'll be talking about valence electrons a lot as we move into Lewis dot structures. Let's do one more. This one's chromium. Okay, and chromium has 24. Now it's a metal, it tends to form cations, but let's say we were asked about the neutral chromium atom. Again, we start down here, 1, 2, 3, 4, and I really suggest that you count these out as you go. 5, I'd also suggest you follow Hoons Rule, even if you know you're going to go past that. 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18. Now, mentally note, 18 is neon. I've filled the 3 orbital. I'm now going to 4, 19, 20, 21. Now, this is important. Hoons Rule, 22, 23, 24. Now, chromium, as a metal, is magnetic. Things like zinc, where all of these electrons are paired up and there are no unpaired electrons, are not. These unpaired electrons are significant because they tell us that that element, as an atom, as a atomic state, will be magnetic. Okay, and if I had drawn this improperly, not following Hund's rule, it would predict that it's not magnetic. And so that's one of the things that becomes important as you go forward. Okay, so there's 24. Now chromium can form a lot of ions. One of the ions it forms is a 2+. You can get others as well. Okay, and how we remove electrons to form ions in transition metals is messy. The other thing that's important to note is when we talk about valence electrons in transition metals, this would be 6 valence electrons. Okay, now the 4s is the highest principal quantum number, but we include d orbitals unless the d orbitals are full, in which case we don't. Okay. All right, so that's essentially how we use AufBau Principle, Pauli Exclusion Principle, and then Hoons Rule to fill electrons into an atom to determine its ground state electron configuration.